substances. Okay, now there is the modern view of magnetism. The modern view of magnetism. Next is the modern view of magnetism. Magnetism. Okay, now what means by the modern view of the magnetism? The modern view of the magnetism explains the magnetic properties of certain substances. According to the modern view of the magnetism, is we know that moving charges constitute magnetic field around them. So if you see, look, the electrons, if we consider the motion of the charged particle, motion of the electron, if you see, look at the motion of the electron. We have two kinds of motion for the electron. And here, one, we have the orbital motion of the electron, the motion of the electron in its orbit. As you see here, look, this is the orbital motion of the electron, as you see, when it is in its orbit. So this produces a magnetic field we call orbital magnetic field. Orbital magnetic field, right? And for simplicity, I'll be knowing it like OB. And then again, we have the spin motion of the electron, motion of the electron. So motion of the electron, you know that electrons spins around its own axis. Also here you see the spinning motion of the electron, as you see, about its own axis, right? This generates a magnetic field. Here in the diagram it is denoted by not OB but by magnetic orbital, and here you have, this causes a magnetic field since it is also a motion, magnetic S, magnetic spin. Okay, so you see, look here, these two magnetic these two magnetic fields, they may be added up together. The magnetic field M is resulting another magnetic field M, right? So this resultant magnetic field, it may be either zero, depends on the orientation of orbital magnetic field and spin magnetic field. This may have some influence, or this may be having added up to the greatest strength. So all the magnetic material are based on this modern view of magnetism. So keeping these things in our mind, we have the paramagnetic substances, we have the diamagnetic substances, and we have the ferromagnetic substances. And for the ferromagnetic substances, along with this, which can be explained on the basis of magnetic domain theory also. Magnetic domain theory. It can be explained as on the basis of the magnetic domain theory also. The paramagnetic substances are those substances which acts like a weak magnet in the presence of strong magnetic field. So they respond weakly to even to a stronger magnetic field. For example, aluminium, like the example include aluminium and antimony, right? And here the diamagnetic substances are those substances which don't behave as a magnet even in the presence of stronger magnetic field. For example, copper and zinc are the best example. Ferromagnetic substances, we have the hard ferromagnetic substances and we have the soft ferromagnetic substances, and they behave as a magnet even in the presence of stronger magnet, even in the presence of weak permanent magnet. Paramagnetic substances behave as a magnet only in the presence of a magnet. Diamagnetic substances have no response whether the magnetic field is weak or strong or whatsoever. Ferromagnetic substances, they once magnetized, they remain magnetized even when the ferromagnetic, even when the permanent magnet is removed. So here I will explain the types or the properties of these substances and how they are being formed. So you see the comparative study of these magnetic material. Here I have the properties. Here I have the diamagnetic substances. Here I have the paramagnetic substances and the ferromagnetic substances. So first, the cause of the magnetism in them. Here in diamagnetic substances, it is the orbital motion of the electrons which produce diamagnetic substances. So the orbital magnetic fields are oriented such that it responds to the external magnetic field, and the substance shows some degree of magnetism in the presence of the sorry, that it is the in the diamagnetic substances. Diamagnetic substances are those kind of substances which do not exhibit any magnetic property, and it is because that the orbital magnetic fields are oriented in such a way that the resultant magnetic field due to orbital motion is zero, and this is why even they do not respond or show any magnetism in the presence of strong magnetic field. There are paramagnetic substances, and in the paramagnetic substances, it is the spin motion of the electrons which is responsible for their magnetism. In the spin magnetic movement are oriented in such a way that they give rise to a powerful magnetic field. So when the external magnetic field is established near such kind of substances, or when such material is brought near the permanent magnet, then they shows some degree of magnetism, right? Ferromagnetic substances, they behave strongly towards even a weak permanent magnet, and this is because of the formation of the domains. Now, what are domains? Here you see that domains are just like houses to small magnetic fields. For example, each domain contains, I think, to the 1 into 10 raised to the power 8 to 1 into 10 raised to the power 10 uh, atoms in each magnetic domains. This is what I'm not sure about. You may confirm it, so don't believe on this because it is statistical and I may forget this thing. So you see here that each magnetic domains contains small atoms within these numbers. And you know that each atom behave as a tiny magnet. So in the absence of external field, all the magnetic domains are disoriented, right? They are randomly oriented. They are what? They are randomly oriented. So when you bring a permanent magnet, all the magnetic domains align themselves in one direction and they behave as a magnet, right? And this is why they respond strongly to the external magnetic field. The response is so strong that even when you remove the external magnetic field, some of the domains still remain aligned. So in the ferromagnetic substances, once the magnetic domains align, they stay aligned even when the permanent magnet is removed. So they even then they remain magnetized when the permanent magnet is removed. This is on the basis of the orbital, on the basis of the orbital motion of the electron, on the basis of the spin motion of the electron, and here on the basis of the domain forms, right? But even when the domains are formed, they give rise or the resultant of still this O orbital magnet and the spin and the orbital magnetic fields. The behavior in non-uniform magnetic field, I explained this to you. I explained this to you how they behave. They form high to low field regions. That is tendency to move from low to high field region and move from low to high field region, as you see, like just the state of magnetization. They are weakly magnetized in the direction opposite to that of the magnetic field. These gets weakly magnetized and these get strongly magnetized. This is what I explained to you, right? So when the material in the form of liquid is filled in the U tube and placed between the poles, then here the liquid level in that limb gets depressed, rise up, and here they rise up very much, as you see. Look, they on placing the gaseous material, you can see this, right? The value of the magnetic induction B, where B naught is the magnetic induction in vacuum. So here you see B is less than B naught, here B is greater than B naught, and here B is far greater than B naught, right? This is the magnetic susceptibility, right? This is what we not our topic here. And here we have the dependence on the temperature, right? That you see does not depends on the temperature. On cooling, these get converted to ferromagnetic material and these get converted into paramagnetic material at Curie temperature, right? So increasing the temperature decreases magnetization, decreases magnetization. Here in you will see increase in the magnetization force. The next important topic is the magnetic hysteresis. The next topic is the magnetic hysteresis. The magnetic hysteresis are the hysteresis loop or curve. Loop or curve. We will explain this, and this is what here the explanation to the idea or the explanation for the ferromagnetic substances. Ferromagnetic substances, right? That is the this tells that magnetization force are they first of all, let me tell you a few important things. One, we have the in order to explain this, we have to understand the magnetic flux density B, magnetic flux density B, or what we can say that the magnetic induction, the magnetic induction, and this is already we know, right? The magnetic. And second important point is the magnetization force or the magnetic field strength. Magnetization, the magnetization, the magnet, yeah, the magnetizing force or the magnetic field strength or magnetic field strength or the magnetic field strength. Here we have one this. The magnetic field strength B, this is very easy, you have already explained, but here we denote this by H, and this H is in fact equal to what? Since we know that this B is equal to what? It is equal to H into mu naught. But for a solenoid, as we know that B is equal to what? Mu naught times N into I. So in fact, this is what? This is our this H, right? That H equals N into I. Where this N I, then it will be called the magnetizing current. The magnetizing current, right? For example, in order to explain this effect, let us consider that a ferromagnetic substances such as iron, like this one, as you see here, this is the like this. Okay, now for example, if we have the that is if we place this inside a solenoid, right, as you see, we want to magnetize and this, right, like this one, and as you see, look, it is placed inside the solenoid with alternating current source, so we have this I. So this is the current, right, that cause the magnetization and demagnetization of this soft iron, right? Now we have one this thing, the flux density. The hysteresis says that, right, it means a Greek word which means lagging. And what does this tells? This says that the flux density B, the flux density B lags behind the magnetizing force, the magnetizing force H, right? The magnetizing force H. What does this means? Long story short, that even when H becomes zero, that is in ferromagnetic substances, where the current falls to zero means the magnetizing force zero, there is still B. The B does not equal to zero. That the material still remains some magnetism even when the magnetizing force is removed, even when the current falls to zero. This is known as lagging, magnetization lagging, right? So this is, look, if we plot the graph between H, as you see, here is our H, here is our B. Now you see that, look, if we increase the current in one direction, for example, from 0 to T by 2 in the positive half cycle. So here you see that as the current increases, what happens? The magnetic flux density increases, right? But it increases to a certain level. After when you increase the current, as you see the current is increased, look here, you see the current is increasing, but the magnetic field strength B does not increase, right? Once when it attains a saturation or a maximum value, right, it does not increase any further. What is the reason? The reason is simple, because once all the magnetic domains align themselves, you see here, look, once all the magnetic domains align themselves, there are no magnetic domains to be aligned furthermore. And this is why even if you increase the current, you do not see any further increase in the magnetic field strength B, right? Now look again, when you decrease the current, as you see here, look, on the decreasing the current, what do you notice? If you decrease the current, then from maximum to zero, you see that B does not fall with the same ratio, right? And even with the decrease of the current here, you see, look, even at the decrease of the current, you see it does not decrease by this way, right? Does not falls to zero, but rather you see that there still, even when the current falls to zero, there still remains some magnetism. This is known as the residual magnetic field, right? This, there is what? There is some magnetic field. Why? Because once the magnetic domains align themselves, they stay aligned even when the magnetization current is removed. They permanently remain aligned. Okay. Now, this, there are another important points which we call retentivity. Retentivity, right? That retentivity, that is H decreases, B reduces, but not zero. If H decreases, as you see, H decreases, look here in this case, you see that as H decreases, what you notice? H decreases as you see, look. You see here that H decreases, but H decreases, but B, H decreases, B also decreases, but not zero. Decreases, but not z, but not zero, but does not become zero. This is known as residual magnetism. This effect is called retentivity, residual magnetism. Okay. There is then another point we call the coercivity. Coercivity, or the coercive force. What does this means? That it is the reverse magnetic field. The reverse magnetic, yeah, the reverse magnetic field, yeah, the reverse magnetization force, right? For which B is equal to zero, for which B is equal to zero, or you may say the reverse current for which B is equal to zero is known as coercive force. And this is what the disorientation, this caused the disorientation of the magnetic domains here. So when you increase the current, look, from T by 2 to 3T by 4 in the reverse direction, right? Sorry, from T by 2 here, that is T by 2, and here from T by 2 to T, from T by 2 to T, like this. So here what is going to happen, that when the current decreases, here you see the decrease in the current, so means the decrease in H, and that what happens, B magnetic flux density decreases until it becomes zero. But when you increase the reverse current further, what happens, then the system gets magnetized in the reverse direction, right? We call this as the we call this as the magnetic saturation, right? Or we call this as the that is the maximum value of the magnetic field in the reverse direction here, as you see. Look, so this phenomena is known as coercivity, that if H is further increased in reverse direction, B attain maximum value. When, that is, when H is increased further, in what? From the value, from the value for which b is equal to 0, for which b is equal to 0 here, like this one. So when you increase it further, what happens? There we again attain the maximum value of b, maximum b in the reverse direction, in the reverse direction, right here. Now again, when the reverse current falls to 0, the same curve repeat itself, and we call this whole curve, right? This whole curve is called the hysteresis loop, right? And this determine the area of the loop. Remember, note the area of the loop determines the work done or the amount of energy required in the magnetization, in the magnetization or demagnetization, demagnetization, the demagnetization of the ferromagnetic substances, ferromagnetic substances over one cycle of AC, over one cycle of AC current, right? This loop for soft, the loop area is small. Loop area is what? The loop area is small. For hard ferromagnetic substances, loop area is large. Means that there is more energy required in orientation and in the disorientation of the magnetic domains, right? This is, for example, steel, and this is, for example, iron. So where we need a permanent magnet, we use hard ferromagnetic substances, such like, for example, in the cranes, to lift heavy load, we make a strong magnet by using the hard ferromagnetic substances. But in substances like transformer, we prefer soft ferromagnetic substances. Why? Because magnetism is not, the magnetism of the core material is not required there, right? We only need them for linking the magnetic flux. So we use soft ferromagnetic substances so that less input of our energy is wasted in the magnetization and the demagnetization of the soft iron core. So this is the end of the today's topic, right? So inshallah, see you in the next lecture, right? This is the end of the unit number 16 also. So thank you very much for being